It's no secret the world turns. Its 24-hour rotation on its axis gives us the definition of a day. Our moon, recently eclipsed in North America, orbits around us. We, in turn, orbit around our sun along with the other planets, and our entire solar system orbits around the Milky Way galaxy. These cosmic revolutions make up the foundation of our existence. But whether you realize it or not, there is another set of revolutions happening all around us every day. These are not some heavenly bodies that were here billions of years before our existence, but simple mechanical devices that we humans invented. Motors. From the gentle purr of your air conditioner to the steady hum of your refrigerator, motors are the backbone of your household. Step outside, and their influence expands further. Cars, elevators, toll bridges, rail cars, and factories all rely on motors of varying sizes and strengths. They propel ships across the ocean, power airplanes through the skies, and drive medical equipment that saves lives. In this world of constant motion, we often take for granted the incredible impact that motors have on our lives. They are the tireless workhorses that keep our society moving forward, a simple innovation that never stops turning, and where the hum of progress is always in the air. Unlike the celestial revolutions we can see from simply looking up, the average motor needs a little help staying true to its purpose, and if not properly calibrated, can lead to annoyance at best, disaster at worst. That's where embedded control solutions come in. Digital signal processing can help control motors and enhance their performance to keep life moving along. A single DS PIC can keep motors spinning correctly and on command for better quality, reliability, and longevity. How could Microchip technology keep these tiny marvels of engineering quietly working behind the scenes, making our existence more efficient, comfortable, and extraordinary? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Alexis Alcott. Alexis is Associate Director of Marketing at Microchip Technology, working out of the DSPIC Digital Signal Controller Business Unit. She joins us today from our global headquarters in Chandler, Arizona. Welcome, Alexis. Thank you for joining us on Beyond the Microchip.
Thanks for having me, Dana.
In the intro, we briefly talked about how motors seem to be everywhere and the fact that they need to be controlled with something as simple as a humble microcontroller. But this discussion all started with a conversation with your daughter, right? How'd that go?
It did. Yeah, I help her with her math homework a lot. And she's a teenager starting to think about career exploration. And she said, I know you're an engineer, Mom, but what do you do? And many other people probably have the same question. You know engineers, but what do they actually do? And so I told her, well, at the highest level or the simplest level, really engineers solve problems. They use math, they use science and creativity, and they solve problems. And sometimes they solve problems that are specialized, whether they're electrical, mechanical, you hear different kinds of engineering degrees. So that's just what kind of problems they're solving. So I said at a certain level, I'm an electrical engineer and I work in the semiconductor industry. So that's kind of specializing. And then the kind of problems that I'm solving are how to control motors in a precise way. And so at this point, her eyes are glazed over because she's purely excited about all this motor control efficiency,
Entranced.
Right? Oh, she's very excited. I told her, that the impact that this motor control can have could actually save the planet. And then I had her attention.
Oh, okay. Say more.
So if you think about it, motors consume more than half of the electrical energy in the world. And so you can think about all the other things you can do to try and save the planet, recycling, buy an electric vehicle, all these things that you can do as a consumer. But really, the energy demands that are out there, increasing our motors to be more efficient might actually have a bigger impact.
So we're assuming that this is something that just spins and it transfers power to another apparatus within. But part that I'm interested in is that you have to control it, that eventually it stops spinning true. What's the breakdown there? How does that happen?
So the most complex part is the start. And so you want to have, a motor has a certain amount of speed and a certain amount of torque. And a lot of times you'll want to have the maximum amount of speed right out of the gate. Think about like a power drill or something like that. And so understanding what all those motor parameters are and how you can start it up is one of the big problems to solve. And then another piece of it can be, that the speed needs could vary over the the use case. So a lot of motors are now adopting more variable speed motor control. And so you kind of have to keep up with how the motor's being used so you know exactly how much to apply.
Different levels of power going in. Is that part of the equation?
Definitely.
Okay. So I did an interesting thought experiment. I knew we'd be recording today. So from the moment I woke up, I've got an electric toothbrush. I've got an electric razor. My wife has a hairdryer. There's a bathroom fan. There's a ceiling fan. I have a coffee grinder downstairs, and I had to open my garage door. That's 7 before I left the house. And then I left the house in a car, of which I'm not even going to begin.
You've got windshield wipers, you've got fans and pumps, power windows. Each of those has a motor.
Got a trunk. Got obviously the air conditioning. A whole number of fans that are internal to that. And then where else do we run into motors just within the automotive space?
Within the automotive space, it depends on the car. Combustion vehicles have a lot of motors in them. And then as you transition over into the electric vehicle space, there's even more electrical motors because you don't have the belt-driven motors.
Right.
You've got motors that help with the sunroof. You've got motors that do a lot of the electrical cooling and heating. One thing people don't think about as you move over to an electric vehicle is you lose the heat from the engine. Previously, when you needed to heat your car, you just could let some of that engine heat through. And now you actually need a heat pump or an HVAC system to create that heat to warm up your electric vehicle. Lots of little hidden motors within a car.
So that's within the automotive space. Where are we talking about, say, in industry?
In factories, the motors that are building the products in our factories can consume, a huge piece of the operating budget for a factory, just the energy costs alone. And so whether it's a conveyor belt or it could be things that are doing mechanical motions, high-end kind of motion control. One statistic I saw said about 70% of the power consumption for a given manufacturing facility can come from motor.
Just the motors.
Just the motors. And so, if you want your factory to make money, having reduced expenses on your power is a big part of your budget. And so that can be, fans, compressors, all that kind of machinery that can benefit from efficiency improvements. One stat I saw said that if we upgraded all those factories to have more high efficiency motors, we could reduce energy consumption globally by about 10%.
Just in efficiency?
Just increases of efficiency. So because you kind of alluded to the pure number of motors we're talking about, even if you just increase the efficiency of these motors by a couple percent, the impact becomes huge.
And we're talking about speed control. We're talking about variance in power generation. Are there other factors to worry about in a motor that you need to control? I mean, what are the parameters of control that we're talking about?
There's 3 basic things that you want to do to increase the efficiency. So there's 3 pieces. The first is just the motor itself. So back in the day, most of the motors had brushes, and then those could be really loud, and their maintenance is an issue. So the newer motor types are called brushless DC motors. And even if you go into Home Depot, even people that don't even have an idea what a brushless DC motor is, it'll be advertised on the box as you're buying certain power tools or things like that at Home Depot or Lowe's. And people just assume that's a good thing, right? It's a kind of a marketing thing. But these newer motor types are much more efficient. And then the second thing that can increase the efficiency is running with that variable speed. So making sure that you're not applying a whole lot more energy that's needed in a given case. And then the third piece, which kind of goes to your question, is the precision. And so those are the fancy algorithms that can run on a DS-PIC or other controller to make sure that we're monitoring and controlling that motor with the closest precision. And there's a lot of very complex algorithms that we won't go into for this audience, but you may have heard of something called field-oriented control. That's one of the examples of algorithms that are part of that efficiency.
Okay, so that brings us to the DS-PIC, which is the digital signal, and then PIC probably has a meaning. Is it lost to time, or is it still in use?
Definitely still in use. So if you look back the history of the DS-PIC, I think the first DS-PICs were introduced back in the early 2000s. So been through many iterations since then. The goal was to have the simplicity of a microcontroller with the processing power of a digital DSP, digital signal processor. So at the time, using DSPs was hard. Using microcontrollers was viewed as easy. And so what we wanted to do is kind of harness the simplicity of, an 8-bit microcontroller, easy to code, easy to use, easy to design, have the increased performance capabilities of a DSPIC. Over time, over the last 20 years, we've seen huge changes in the landscape for the controller space. What remains is really that the 8-bit is the very hardware-centric view of the world. If you're using an 8-bit microcontroller, it's because usually it's a single thing that it's controlling and doing. And it's very hardware-centric in how it interacts with the world. The software is kind of a small piece of the design usually. And now everybody talks about 32-bit microcontrollers have grown in popularity a ton over that 2-decade time frame. And the 32-bit space has a much more software-centric view of the world. Lots of program space, lots of algorithms, lots of connectivity. And a lot of the things that 32-bit microcontrollers go into just take up a lot of code. And that's really helpful for IoT applications, consumer appliances, and things like that. But as you put all that software overhead on something, it kind of loses its ability to react really fast to things that are like an interrupt or something that is a kind of a real world response. So where the DSPIC comes in is it tries to give you that hardware-centric, low latency, fast response time to things that matter. So the applications it tends to go into are things like motor control, where you've got something that's spinning. You need to make sure you react to it very fast. There's safety concerns. Other examples would be power conversion. There's no time for latency or delay in a power conversion system, or other kind of real-time world applications like maybe actuators, sensors, and things like that. So the DSPIC doesn't go into a whole lot of general purpose applications. It finds its home in much more specialty real-time control applications.
Critical real-time stuff, right?
Exactly.
Like a motor's designed to do its thing forever, assuming.
Yes.
But you certainly don't want a motor to stop for any reason.
Exactly. Yes.
So there's some of the examples that I listed earlier. Those are the obvious ones that I'm thinking of. Are there some unobvious motor applications that I'm thinking of? Are there things that maybe have motors that maybe we never realized? Is it something that's, hiding right under our nose?
They are often hiding right under our nose. I think the ones you mentioned are perfect. I kind of had a list of where are the motors that we interact with on a daily basis. And so I think the morning time ones that you hit, I also had a blender on my list, the appliance space. You make your morning smoothie. And then your commute to work, certainly car has a lot of motors in it. And then you get to work, elevators. In a meeting room, you have projectors that has microcontrollers in it.
That's right. They got a fan in them. The
screens that go up and down have motors in it. The fans that control our heating and cooling, all of that has motors in it. And then, you get home from work and all the things that are in your house, your washing machine, your vacuum cleaner, your rage hood fan has motors in it. And then things like your power tools in the garage, or even things you might not think about. I don't know if you've ever played around with those crafting machines that you can die cut stickers, you can die cut things that iron on. There's over 100 motors in a typical home.
Wow.
Toys, lots of
have motors, that's for sure.
Everything's moving and making noises. So that's I'm sure there's other examples, but those are a few.
Right. So you hinted on something. There's probably motors working on motors. Everything's got a fan in it because everything's got to be kept cool. So every electrical system is probably generating heat. A motor itself probably generates heat. So you might have a motor for a motor. And then just wandering around. If it hums, if it clicks, if it whirs, it's probably got some kind of motor in it, right?
Yeah. And think about like the unintended motors that you're interacting with. So we save everything in the cloud now, right? That actually has to physically get saved somewhere.
Right.
So where's that data center where all your cloud-based computing is being stored? The energy consumption from data centers has doubled over the last decade or two as we have this huge shift towards cloud-based computing. Just imagine how many things are needed to cool down those data centers. And then you add in AI and ML into the mix, and the data center space is going to need to increase drastically.
Yeah, it's
drastically.
Only growing. Okay, so we've got kind of a motors everywhere. I'm sure we'll run into one on our way out the door today. I could probably pick out 2 or 3 just in this room, from the paper towel dispenser to the projector to, I imagine there's a a motor in the water dispenser over there, but the idea that they're so much a part of our modern existence that we probably take a lot of that for granted. And each one of those motors has to be controlled smartly. So you want to be able to do it at an effective cost, but you also want to be able to do it with something a little bit more intelligent than your basic microcontroller. So it's kind of the best of both worlds. Is that what we're getting to with the DSPIC?
Exactly. So, and the silicon itself has capabilities on it with, the processing power of the real-time control. It's got a lot of specialized peripherals that kind of incorporate and loop right back into the core. So that's things like analog to digital converters. That's the fancy words for how do we interact with the real world and get input. And then there's other peripherals called pulse width modulators or PWMs, and that's how do we kind of respond back to the world. And then the core kind of sits in the middle and does all the smarts, all the processing of information. So all that silicon exists in a wide range of capabilities, from performance to how many of these inputs do you need? How many of the outputs do you need? And so there's quite a robust silicon portfolio, but it's supported by a lot of ecosystem because the silicon itself can be pretty hard to design. So you need to have algorithms, dev boards, app notes, users guides, a lot of that ecosystem to help people do those types of designs.
Let's talk about power. A lot of people talk about electrification and the move towards electric vehicles. Does that impact motors in a car?
It sure does. There's over 1 billion cars in the world. And if you assume that every car has at least 40 motors, we're talking about 60 billion upside of that motors in cars.
Just cars.
Just in cars. So if you are applying efficiency in those motors, the amount of energy savings, 1%, 2%, times those billions of motors, that is a huge potential for a global impact. And we talked about some of the different places that motors are hiding in our cars, but moving all those functions into higher efficiency can also reduce weight in the car. And that can lead to longer range in electric vehicles. You can have lower emissions and higher fuel efficiency if it's a hybrid or combustion engine car. And where a lot of the BLDC motors benefit in a car are things that are going to run for long periods of time. Windshield wipers. If it's raining, those are going to be on for an hour during your drive. Cabin heating. That's something that stays on, for a long period of time. Anything that's a blower or a pump, those type of applications really benefit from the BLDC motor type of efficiency. And so we're talking about, efficiency rates in the mid 90s to higher 90%. So if you think about, there's kind of a point of diminishing returns that, to take something from 20% efficient to 50% efficient is pretty easy. But after you're at 92, 93, 94% efficiency, cranking that little bit of increased efficiency is quite a bit of work. But in these cases, when we're talking about doing that across so many different motor types, then it can be
compounds itself,
impact.
right?
Exactly. Yeah, a huge compound effect.
Okay, so what? So we talked about factories earlier, and we talked about automotive. Are there other markets that dominate motor energy usage?
Those are the big two.
Okay.
They have graphs out there that you can show where's all the energy being consumed, and transportation is the biggest category. So cars is a big piece of that, as well as airplanes, trains, subways. Kind of think about any way people get around other than their car.
Well, yeah, we're electrifying trains. We've already electrified cars. We're probably electrifying boats. We're electrifying aviation. Space, I think, is probably the only one left that hasn't been fully electrified yet, but that's physics.
Quantities aren't there yet.
Separate talk show. But we're looking at a lot of different areas where the electrification is going to require these types of efficiencies, right?
Definitely. And so that's one of the biggest categories. And then factories is the second. And then the third would be probably residential heating and cooling. A lot of the same technologies that are used in our homes or in factories for the heating and cooling have a big impact. And there you'll start to see things with sustainability impacts. You've got somebody goes out and buys an electric vehicle, they come home and they put the charger in their garage. And then usually you want to get some kind of battery backup system because a lot of those batteries are bidirectional. You have the solar panels on your house and you kind of have a little bit of a self-sustaining ecosystem. there. So there's a good crossover between some of this, motor control space and the sustainability space as well.
Mm-hmm. Yeah, absolutely. All right. So suppose one of our listeners has a use case for this technology. Where would they go? How could they adopt it? Where should we send them?
The best place to start is on Microchip's website. You go to www.microchip.com/motor.
Motor. Okay.
Pretty simple.
We'll put that in the show notes.
If you go there, there's examples of starter kits, development boards, some of the specialized tools in the ecosystem. We have a tool called Motor Bench Development Suite. It's like a GUI that runs on your PC, and it helps with the motor control design, make things simpler. But the biggest piece there on that website, you'll see a link to a whole bunch of reference designs. And so we try and take certain key markets that are out there that are complex, and we build up the motor control portion of those designs. So we've got reference designs out there for vacuum cleaners, power tools, refrigerator compressors, air conditioners. So we're not building up a whole vacuum cleaner, but we're taking the motor control portion of the vacuum cleaner and creating all the boards, the schematics, the code that would be needed so that people designing in that space can take that as an example, and maybe it gets you about 80% of the way there, and then they add in that last 20%.
Yeah, so we've heard reference design mentioned a couple of times before. What you've just given a pretty good example case of what it is, but is there a single definition of what a reference design is and why it's important?
I don't know if there's a single definition. I think for Microchip, what we try and do is create the boards, the software, and all the supporting documentation so that somebody can jumpstart their design. And it's not a single product. We try and include all the surrounding components that are necessary to build that function. So like one example is we've got an e-scooter reference design. Right. It's not a full e-scooter, but it's the full e-scooter motor control. And so it doesn't just include a DS-PIC. It includes all the MOSFET drivers, the power management, all the surrounding gate drivers and connectivity that are needed for that piece of the e-scooter design.
So you said it jumpstarts a design. Would that allow for them to change things up accordingly for their individual application or their project requirements?
It would. And what it will do is it gives them all the software so that they can customize it and they can add their differentiation into the end design.
So we're going to be experiencing kind of the electrification of everything, which is another episode we're going to be talking about. This will eventually lead to a higher need for digital signal processing. It'll lead to, of course, more motors. Do you have any predictions for the future of motor control or DS-PIC, or how the evolving technology could enhance the human experience, like the examples we talked about today?
I do. I think there's two factors at play. One is government legislation. And we talked a little bit about sustainability, but I think there's a lot of initiatives out there that are trying to help navigate people on the right direction so that we use our energy more wisely. And so I think that efficient motor control will be a key piece to solving that problem and meeting some of the goals of that legislation. And I think the other thing that's still a little bit unknown is the impact of AI. And so I think when most people think about AI and solving problems, they think bigger. They think about more esoteric ideas of how we're going to use AI to change how we do things. I think the bigger impact for AI could be the things that we're already doing. One example would be predictive maintenance. Got a motor that's running. I like to use the HVAC example since we live in Arizona. It's 120 degrees, and that's always when the air conditioning fails. Is typical. The worst possible day. But if you knew ahead of time that motor was starting to get flaky, you could get the maintenance guy out and do it in a proactive way, because when yours goes, that's when everybody else goes, and then you got to check into a hotel because they can't get to you for 3 or 4 days. So predictive maintenance, I think, is a big thing to try and fix inefficiencies and potential failures. Think about the predictive maintenance impact or use case at a factory. You know, if a motor goes down, a whole line is lines down.
That's right.
Time is money, right? So I think that has a big potential impact for AI and ML. For the design effort itself, a lot of the design effort is spent trying to commission or figure out what are the parameters for a given motor. Every motor kind of has different parameters. So the designer has to do that work. But with machine learning algorithms, self-commissioning could be much, much easier. And then adaptive control is probably a big piece of it, where the AI or ML algorithm could actually reside on the DS pick and kind of keep up over time as the load changes and as the motor parameters slightly change, to be able to kind of adjust over time and keep that efficiency as high as possible.
So it would lengthen the lifespan of the motor.
It would definitely lengthen the lifespan and decrease the amount of maintenance.
Mm-hmm.
So probably not the use cases most people think of when they think of artificial intelligence, but I think they could have a big change on the motor control landscape.
I think it helps to have that kind of perspective. The term AI is kind of this nebulous cloud that has so many things in it. And, the headlines will tell you that AI is just something that's going to come take everybody's job. Whereas there are opportunities for analysis and optimization like you're talking about. There's ways to improve efficiencies. So it's nice to see that even in the small corners of our little world, there's going to be things that AI is going to be really, really good at. And I guess lengthening the life of a motor, you really don't appreciate until that motor stops.
Exactly. Whether it's that coffee grinder in the morning or
the heat pump or the air that's coming in the middle of Phoenix summer.
Exactly.
Any final thoughts, Alexis?
Yeah, I think a lot of people are talking about sustainability and building products that are green or more energy efficient, and really trying to solve the carbon emission problem. Think about that impact of what 1 or 2% increase in motor control efficiency could do if we applied that to every motor in the world. I think that it has a huge global impact that we could try and use to reducing energy consumption around the world. There's a lot of focus on generating cleaner energy, but we also need to be good corporate stewards of the energy that's out there and make sure we make the best use of what's already being generated.
Thank you, Alexis.
Thanks,
Appreciate
Dana.
you joining
It was
us.
fun.
Alexis Alcott is Associate Director of Marketing at Microchip Technology. She specializes in defining and launching real-time control solutions for automotive, industrial, and sustainability markets. She joins us today from our global headquarters in Chandler, Arizona. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.